Hi there! Welcome to the 28th episode of the Synth project, where we are going to build a synth together. In this video we are going to be building an oscilloscope module for our analog synth. If you have watched my previous video, you'll know that I already covered the oscilloscope unit and how it works. In this video we are going to be putting it all together and seeing how it works. As always, I'm going to assume that we have some basic soldering skills and that you are familiar with the basics of electronics. If you're not, I recommend checking out some of the other videos on my channel. And now let's begin. This is a view of the module case I designed for the Synth oscilloscope. The front features a hole for the oscilloscope display and its controls, including 3 switches on the left side and 5 push buttons on the right side. Below the display there is a hole on the left side that will accommodate the on-off switch for this unit. On the right side, 2 holes are available for 2 jack sockets. One socket is for inputting the signal to visualize on the scope, and the other one is for passing through the signal to another module of the synth. The back side of the case features 4 embedded spacers, which serve to lock the oscilloscope PCB in place using screws. Additionally, there are 4 holes located on the side panel to hold in place the power supply circuit, which converts the plus 12 volts available on the power rails to the plus 9 volts required by the oscilloscope. Here you can see the accessories I need to reach the switches and push buttons on the oscilloscope PCB, which would otherwise be inaccessible from the front panel. These components will be inserted from the back side of the panel holes, and then the PCB will rest on top of them. Later I'll show you how these pieces fit together. Please take note of the holes along the bodies of the 3 elements that will be used to control the switches. The switch controls will be inserted into these holes to enable their operation. Finally, these are the graphic elements that will be printed on decals and added to the front panel. Now I present you the completed case for the oscilloscope module. This area is where the oscilloscope PCB will be located, and the display can be seen through the window. There are holes for the switches that control the sensitivity, volts per division and vertical axis multiplication factor, and the coupling switch on top, where we can choose to connect the input to ground or connect it directly to the input for DC signals, or decouple the input signal with a capacitor in the case of AC signals. On the right side there are 5 holes for the push buttons that control the various functions of the oscilloscope. On the bottom we have the hole for the power switch that turns the oscilloscope on and off, followed by the 2 holes for the input signals and the pass-through. We will use the input jack to pass the signal to the oscilloscope for visualization, while we will be using the pass-through to send the same signal to other modules of the synth. On the back we can see the same holes for the switch and the jack sockets. The oscilloscope PCB will be held in place using screws inserted into 4 embedded spacers, so the display will show up on the front side along with all the controls coming from the holes. Here is one of the pieces that will be used to control the switches, which will be inserted into the appropriate hole from the back. The other piece is used for the push buttons. This is the power supply schematic for the oscilloscope module. It is built around an LM7809 voltage regulator, which will convert the plus 12 volts from the power rail into a more suitable plus 9 volts for powering the oscilloscope. The capacitors C1 through C4 are used to filter out any possible ripple and noise that may be present in the input power. Diode D1 provides reverse bias protection in case the input voltage to the regulator collapses faster than the output voltage when the power supply is turned off. Diode D2 acts as a clamp diode, protecting the regulator from output polarity reversal during startup and short-circuit operations. There is also a switch to turn the power supply and consequently the oscilloscope on and off. J1 brings the power from the synth rails, and J2 powers the oscilloscope directly. Here is the power supply circuit mounted on a perf board. I opted not to create a PCB for it given its simplicity. The LM7809 is mounted on a heatsink, and this socket is connected to the power rail to carry the plus 12 volts into this circuit, and the other socket will connect to the oscilloscope to power it up. The circuit includes protection diodes D1 and D2, and finally there are 4 capacitors, 2 per side, to filter out any possible electric noise. And of course, I forgot to connect the switch. Here it is now, connected in series with the plus 12 volts coming from the power rail. To test the power supply, connect a voltage of plus 12 volts between the first and the third pin from the top of the left socket, with the positive on the first pin. In this case, the voltage is being taken from a workbench power supply set to 12 volts. The output voltage can be measured on the other side of the power supply using a multimeter. At this point, the switch is supposed to be in the off position, and so there should be no output voltage on the circuit. The multimeter, in fact, shows no voltage. After turning on the switch, the output voltage can now be measured again. In this case, the multimeter shows a steady 9 volts output from the power supply. Very good. Next, we need to make some minor modifications to the oscilloscope PCB. To power up the oscilloscope, we'll be using this connector instead of the jack on top. This wire will be used to connect the 2 boards together. For the input signal, instead of using a BNC connector which takes up a lot of space, I soldered these 2 wires to the ends of the BNC socket. The white wire is connected to the center of the socket and carries the actual signal. The black wire is connected to the ground of the PCB. The other end of this cable will be connected directly to the input jack socket and the through socket on the front panel. The black wire goes to the socket ground, and the white wire goes to the signal pin. The first step is to apply copper tape to the back of the front panel and the internal part of the side wall. I choose a tape with a particular width and used a single piece between the back panel and the side, and another piece to complete the area coverage. Make sure to avoid any air bubbles under the tape and flatten it as much as possible. Some wrinkles are okay as long as they can be flattened out. Only the area where the jack sockets, switch and power supply board will be mounted needs to be covered with a copper tape. The oscilloscope PCB does not need additional EMI shielding, as the shield has already been integrated into the PCB design. Using a soft cloth can aid in flattening the tape onto the walls of the case. Once that's done, the next step is to uncover the holes where the components will be mounted, the 2 jack sockets and the switch. To mount the components onto the front panel, start with the through socket, followed by the input socket, and then the switch. Ensure that the switch is oriented correctly according to the on-off labels on the panel. Lastly, it's important to take care of the power supply board, to prevent the wire connecting it to the switch from breaking. Start by attaching 4 spacers to the board. To prevent the spacers from being pulled inside the holes, add a washer between each spacer and the board itself. Once the spacers are mounted, attach the board to the side panel using other washers on both sides to prevent the screw heads and the spacers from getting into the holes in the panel. When inserting the screws, do not tighten them at the beginning. Tighten them only after all the screws are inserted, otherwise it will be more difficult to insert them all. And also route the cable between the switch and the board so that it will not get in the way while working on the oscilloscope PCB. Before attaching the oscilloscope PCB to the panel, connect the power cable and insert the push-button extensions from the back of the front panel. Then insert the switch extensions onto the switches themselves. Carefully lay the PCB onto the panel, making sure that all the extenders are visible and reachable from the front panel. Then apply the 4 screws to hold the PCB in place. And again, do not tighten each screw right away. Insert them all first, and only when they are all in, tighten them up. Do not apply too much force. It should be enough for the screws to dig their way into the plastic spacers, but not too much to break them. Finally, clean the display with a soft cloth to remove the fingerprints from it. The last thing that needs to be done now is to connect the power supply cable to the power supply board and then solder the input cable onto the jack sockets. Now I will strip the end and the middle section of the input cable, so that it can be used to connect both the input and the through sockets. After stripping, I will solder it to the two sockets, starting with the first and then the second. Once the soldering is done, I will reroute the cables to keep them out of the way. Using zip ties is an optional step to keep the cables neatly organized. And now we are ready to install the module in the synth rack. I've chosen to place it on the upper shelf on the right side. Since the rack has wooden rails, it's always better to make pilot holes to help the screws grip into the surface of the wood. Before actually screwing the module in place, we need to connect its power supply to the power rail, and once that is done, we can position the module and fix it in place using the 6 screws. Begin by inserting the screw in the upper left corner. As always, it's important not to tighten the screws immediately. Instead, screw them in a little bit first, before tightening them up. It's time now to test the oscilloscope, and what better way to do it than by visualizing waveforms created by the synth itself. Let's start with a sine wave generated directly by the VCO. Adjusting the time base, and here is the waveform displayed on the oscilloscope. Let's now increase the frequency, and now reduce it. We can also increase the frequency and adjust the time base to show only a small number of periods on the display. Now let's take a look at the measurements done by the oscilloscope itself. We can see a peak-to-peak voltage of 4.9 volts, which is correct since we were expecting a value of about 5 volts. The frequency is 0.8 kHz or about 800 Hz. Let's decrease the frequency and adjust the time base. Good. Now we can see that the frequency is about 26 Hz. Next, let's switch to the pulse signal. Right now it's a perfect square wave, not considering that it is not centered around the 0 volts value. Changing the duty cycle, switching to AC coupling. And we can now see that the internal capacitor of the oscilloscope in series with the input is causing distortion of the signal itself. Let's remove the measurements from the display. And now, switching back to DC coupling, the signal is shown correctly again. We can see that changing the duty cycle from one end to the other causes a wide range in the shape of the pulses. Now let's test the sawtooth waveform. Here it is, displayed on the oscilloscope screen. Adjusting the sensitivity to 0.1 volts, and changing the output level on the VCO. Now adjusting the time base to get a better view of the waveform. Now I am going to remove the signal entirely. As you can see, the horizontal line is not aligned with the arrow on the center left in the display, which indicates that the oscilloscope is not correctly tuned. We need to run the auto-tune procedure to fix this issue. To calibrate, we need to follow a few steps. First, we need to connect the oscilloscope input to ground using the CPL switch. Second, we need to push the select button to highlight the arrow on the center left of the screen. And lastly, we need to push and hold the OK button for a few seconds until the horizontal line aligns with the left arrow. Now that the calibration is complete, we can move the CPL switch to the DC coupling position. And as you can see, the horizontal line remains aligned, and we should be able to see waves perfectly centered on the display from now on. Let's adjust a few more settings and we have a nice sawtooth waveform. I now use the VCO switch to invert the shape, and we now have a ramp waveform. Now let's switch back to the pulse waveform, and you can see that as I play with the duty cycle, the vertical position of the waveform does not change, as it should. Let's try now mixing different waveforms on the VCO itself. Starting with a triangular waveform, I'll add a pulse waveform on top and adjust the duty cycle. See how the shape changes by changing the duty cycle of the pulse. Next, I use frequency modulation using the LFO on the VCO. And you can see how the frequency keeps changing. Finally, I will use the ADSR module to change the amplitude of the waveform over time. To do this, I'll use the keyboard to provide the gate signal to the ADSR module, and I will also inject the output signal into my amplifier so we can see and hear the waveform at the same time. What do you think of this waveform? In conclusion, we have successfully built and tested an oscilloscope for the modular analog synthesizer. Throughout the video, we have demonstrated how to assemble the module, connect it, and visualize the various waveforms provided by the synth itself. We have explored different ways of mixing and modulating the waveforms using various modules such as the LFO, the ADSR, and the keyboard, and overall this has been an exciting and rewarding project, and I hope that this video has been informative and helpful for anyone interested in building their own synth. In the next video, this series, we will be exploring a new module. There are a variety of modules that I am considering making, and if you have any suggestions or preferences, please feel free to share them in the comments section below. Your input is greatly appreciated. And while looking forward to work with you again in the next video, I leave you with my usual happy experiments.